Hello, everyone, to a new session of basic engineering. What I was going to start today is moments or torques. So let's define first what the word moment means. So when I say moment, we say it is the tendency of a force to produce rotation. And the rotation is always about an axis. And this axis is perpendicular to the plane of the force. We'll see what that means because it's still a little vague. Notice that the rotation is always about an axis. Sometimes when we are at 2D or even in 3D, we say, find the moment that the force produces about point O. Really, the moment is not about a point, it's about an axis. But this axis, we are telling you, the axis is passing through point O and perpendicular to the plane that contains the force or the forces. So, excuse me, when you look at a door, for example, when you open the door or close the door, you are rotating the door about the axis of the joints, a vertical axis. Okay, so that's the same. If I'm looking from up, so if I take a section and look from up, I will see that the axis of rotation is a point, right? It is a line that passes through the joints, but when you look at it from the up, from above, you see a point. That's why sometimes you say find the moment about a point. So let's take a very simple example. Absolutely simple example. So if I have some kind a line here, this point we call it O. Notice that's an axis. And then I apply a force, and let's say the force is vertical or perpendicular to this line and this force F. And we want to calculate the moment that this force produces about point O. First of all, the moment is a vector. And as a vector, it has a magnitude and it has a direction. Like we said, the direction is perpendicular to the plane of the paper and passing through O. We apply the right-hand rule to see whether it's going up positive or down negative. And you can see that you can think of it as if I had like a nut here and I attach like a wrench to it. And then I'm pushing the wrench like that. So it will start rotating and the nut will move up. So that's a positive moment. We don't need to try to do that. We see that if the rotation is going counterclockwise in 2D, counterclockwise is positive because it produces emotion of the nut going up. Or if it's a bottle cap and I'm rotating it the same way the force is applied, the bottle cap or the bottle will open or the bottle cap will move up. And of course, clockwise is negative. That is called the right-hand rule. Now, let's assume that, or if I want to calculate the moment about O, and I know the distance, that distance is D, which goes from O, say, to A. And I can say, because in 2D, the moment will always be about the Z-axis, right? It's either going up, positive Z, or going down, negative Z. So we sometimes you don't represent it as a vector. So we don't say, for example, F times dk. No, we can say just positive FD or a negative FD if the F is going in the opposite direction. Okay? But we know that the positive or the negative are positive K or negative K. But again, for simplicity, sometimes we just drop the vector part. However, if I want to solve this using math, like just using matrices, and let's assume this force, just to give, let me give you an example. Let's say I have a beam like that, and this beam is fixed in a wall or something, and it has a piece going up. And let's write some numbers. So let's say this is 5 meters, and this is 2 meters. And here I have a force of magnitude, let's say 100 Newton. And it's not along the line. So let's say this is 3, 4, 5. And I want to find the moment about O. There are two ways. A way similar to what we did here and say force times the distance. So in this case, I'm going to break this force into two forces. One of them is horizontal. Notice the horizontal is 4 out of 5. 4/5 of 100 is 80. So I'm going to replace this inclined force by a force that is 80 Newton horizontally to the right, and 60, 3 over 5 is 0.6 times 100 is 60 Newton going down. And then I say, this one is going clockwise, and that one also is going clockwise, right? So the moment here would be a negative moment, 80 times 2, and clockwise, so negative again, 60 times 5. 80 times 2 is 160. 60 times 5 is 300. So I get negative 460 Newton meter. Meaning negative 460K Newton meter. Please be careful. This is a common mistake. Many students would say, this is 80 times 2 because the force is to the right, so it's positive times 2, but the 60 is negative because it's going, no. We are not doing forces, we are doing moments. So a force moving to the right or to the left can produce either positive or negative moment. How is that? Suppose this 80 was rotating about this point or that point. It's below, so it's going counterclockwise, so it would produce positive moment about this point, but it's going clockwise about O, so it's producing negative moment about O. Likewise, the 60 is producing negative moment to any axis to its left, but if I'm taking a moment about this point, the 60 would produce positive moment counterclockwise. So I don't care how the force, the sense of the force, is it to the right, left, up, down? I don't care. What I care about is the rotation. Is the rotation clockwise negative or counterclockwise positive? This is a very common mistake for beginners, so please be careful. I can do the same thing if I have an inclined force in 3D, but it becomes so tedious and many students cannot visualize it in 3D. So instead of that, we use matrices and cross products. How do I use a cross product? The definition of the moment now as a vector, notice these are vectors. I can write this as negative 460 K Newton meter, right? And we said we just drop the K because we know it's always, a force in XY would produce moment in the Z. So either positive ZK or negative Z, which is negative K. But the moment as a vector, if I write the moment as a vector about point O, listen carefully. At all times, we say force times distance, force times distance, force times distance, force times distance. However, when we do the vectors, we say R cross F. The R comes first, then the force. If you write the force first, you will get a negative answer, the opposite, exactly opposite answer. So please be careful. It's R, and R here is referred to as the position vector. And it always starts the same as where you are taking the moment. I'm taking a moment about O, so the R starts at O. But where does it end? Any vector has a starting point and an ending point, or initial and terminal, or tail and head. So the tail of my vector is O, always, where you are taking the moment, always there. Many students do it the other way around, because they say force times distance, or they write the vector like that. No, the vector is always where you are taking the moment. And where does it end? It ends anywhere along the line of action of the force. Here is my force, so I can use any point along this line. And you say, but I don't know points about this line. I know. So that's why we are going to take the point A. That's the easiest one. If you want to do geometry and see where this line, for example, will intersect the horizontal line somewhere here, and you do the math to find, that position vector, yeah, you can use it. Okay? Any point, and you will see why later. Or you can extend this line up here until it is vertically above O, and you find vector O, say B, if that point is B, if you know how to find that. And of course you can, but it's a lot of work, and it's unneeded work. So let's see how we are going to do that. We are going to say my moment equals, as we did in the previous session in math, I, J, K, maybe a different color. I'm going to write IJ. Position vector first, not force first. OA is 5I plus 2J plus 0K. 5, 2, right? Do you see that? I'm going from point O to point A. I move 5I plus 2J. And then the force is 80I negative 60J 0K. 80 negative 60. So my moment equals, like we learned, we are going to use two brackets with two pairs of parentheses in between. I get 0I plus 0J negative 60 times 500 times 5 is negative 300K. Negative 300K, which is this guy. And then you say minus. You go in this direction, 0I, 0J, 160K. Negative times positive is negative 160, negative 160. So when you do the math, you'll get negative 460K Newton meter. Very simple, right? So in 2D, sometimes it's easy to find the moment without matrices. So just go ahead and do that. Instead of determinants, I meant not matrices. And sometimes it's more complicated, so it's easier just to write it in vector form all along. Now to complete that, let me give you another example. So let me say I'm going to draw like a 3D thing. So let's say we have here a support, and there is like a pipe going up, and then it's going inclined like that, and then it's going to go horizontally like that. So, so this is like a post, and then there is a pipe going like that, and another pipe going like that. So they are in a higher elevation. So let's say, again, just for simplicity, let's say this is 3 feet. This is 4 feet. And that's 5 feet. It's not drawn to scale, but so these two pipes are at a higher elevation than this support, but they are on the same plane. Okay. And let's say I have two forces here acting. One of them says F1, one of them is F2. And let's say I know what they are in vector form. So this one says 100I minus 120J plus 75K pound. And this one is, let's say, it doesn't matter really. You can have it as negative 200I plus 250K plus J. I'm sorry. Why am I doing K? Keep writing K. Plus 100K pound. And I want to find the moment that produces, let's say this is point O and this is point A. What is the moment about point O that these two forces produce? In fact, the best way is to find the resultant of these two forces and say the moment produced by the resultant is the sum of the moment produced by each force. So let's find the resultant here, which is F1 plus F2. And I'm just going to add. So 100 minus 200 is negative 100I. Negative 120 plus 250 is positive 130J. And 175K pound. So now my moment, notice that the moment, as we said, equals R cross F. F here would be R, right? Because instead of saying R1 cross F1 plus R2 cross F2, it's the same thing. And R here always starts at O, because I want the moment about the axis passing through O and perpendicular to these two forces. Excuse me. And it ends anywhere along the line of action of the forces. If I'm going to use these two forces, and since these two forces pass through point A, then it makes sense to say ROA. There is no reason to try to find a point here and a point there and say ROB cross F1 plus ROC cross F2. And also, how can you find these points? Very complicated, because that force in 3D is somewhere, it's very hard, right? There are ways to do it, but it's a waste of time. Why would you do that? So in order to find the moment, like always, we are going to say I, J, K. opposite, different color. R comes first. So if we are saying, maybe we should have done that first. We should have said, this is the X, this is the Y, this is the Z. Notice you are not free to pick any three lines. You have to, if I turn from X to Y, I move in the positive Z. So if I make this X and that Y, I cannot make that Z. Okay? Turning from X to Y, you are moving along the positive Z. So in this case, X is 4, the I is 4, J is 5, and K is 3. 4, 5. The forces, I have negative 100, positive 130, positive 175, negative 100, positive 130. So the moment equals, I'm going to open two pairs of parentheses with a negative sign in between, and then close the brackets. Maybe I should have made that one. Okay, I go in this direction. 5 times 175 is 800. Yeah, it's 875I. Negative 100 times 3 is negative 300J. And 4 times 130 is 520, so plus 520K. And then I move in the opposite direction. 390I, 600J, positive. Of course, it's negative, but I'm talking about inside the parentheses, and negative 500K. Pound-foot or foot-pound. So 875 minus 390 is 485. Negative 300 minus 600 is negative 900J. 520 plus 500 is 1020K pound-foot. That's the moment. You tell me, okay, can you find this moment as a magnitude and direction? Absolutely. You can use the Pythagorean theorem, and you say, what is the square root of 485 square plus 900? Notice it's plus negative 900 square plus 1020 square. Under the radical, you get 1444. So the moment as a magnitude is 1444.17 pound-foot. And then you can find theta x, theta y, theta z, like we did with any vector, right? So I can say theta sub x equals, theta sub y equals, and theta sub z equals. You get r cosine, so inverse cosine of 485 over that. This is 70.38 degrees. Theta y is negative. So you have to write negative 900 over that. And of course, that would be an obtuse angle, 128.55 degrees. And finally, you get inverse cosine. That's a smaller angle, the smaller one, 1020 over 1444. And it equals 4507. Use two decimal places. And of course, the sum square of the cosine of these angles will always add up to 1. That's common sense. One last thing. Sometimes the problem may ask you, can you find the perpendicular distance between O and R, the line of action of these forces. Notice that these two forces act in a plane that contains F1 and F2, meaning if you draw a parallelogram, this is R. So if you drop a line from O perpendicular to R, can you tell me what is that distance? And you say, oh my God, are we going to do geometry here? It's so hard. How? No. The moment equals the force times the perpendicular distance between the axis and the line of action of the force. Again, the moment, the magnitude of the moment, look here. The moment about point O is F times D. Why F times D? Because D is the perpendicular distance from O to the line of action of the force. If the force is inclined, I break it into two. I multiply 80 by the perpendicular distance from O to the line of action of 80, which is that distance, the 2. And I multiply 60 by the perpendicular distance, which is 5. So this moment, 1444, equals the magnitude of the resultant, magnitude of this force, times the perpendicular distance. So if I want to find R as a magnitude, I would say it's the square root of 100 square plus 130 square plus 175 square. It's 239.84 pound. So perpendicular distance equals moment over resultant. It's 1444.169 divided by 239.8. Notice usually they don't ask you this question, but I want you to understand that really, if I know the perpendicular distance here, I can multiply the magnitude of the resultant by that, and I would have gotten the magnitude of the moment. And that distance is 6.02 feet. Notice that the distance OA, which is not exactly that, should be close to this, right? But again, we know that 3 square plus 4 square is 5 square or 25, plus 5 square is 50. The square root of 50 is 7. Distance OA is 7.07, but the perpendicular distance is slightly smaller. It's 6. So the distance OA is 7, but that's not the perpendicular distance. That's inclined in space. If you want to find the perpendicular distance, you get exactly 6.021. Again, if that was a little complicated, don't worry. Most like 99% of the time, you will not be asked this question. But if you somehow were asked to find the perpendicular distance between the moment, between the force and a point where you take the moment about that point and divide it by the magnitude of the force. We found the moment as a magnitude. We have the force as a magnitude. Divide this by that. It gives you the perpendicular distance. I hope this was clear. We will take more examples in the next session, and then we are going to talk about couples. And once we are done with couples, we can start moving to look at types of supports in 2D and 3D, so we can start analyzing actual structures like trusses, frames, machines, and that would be the most important part really of the course. So we are building all of that. This is a foundation using forces and vectors and moments to be able to do that, to analyze the structures. I hope this was helpful enough for you. And if you have any questions, again, don't forget to drop me a comment in the comment section, and I will try to come back to you as soon as I can. Thanks, and have a great day. Bye.